Alright, new haircut, new video. Hey everyone, this video is about Lagrangian mechanics. We will first see what this principle is about, where it came from, and how we can actually use it. But then in the second part of the video we will do a very basic Python implementation of the mass spring system. So, hope you enjoyed the video, leave a like, subscribe, and let's go. Alright, so the Lagrangian mechanics is actually a mathematical framework that can help us describe a system or the motion of a particle within a system in a very simple and elegant way. Now, one question may arise. Why do we actually need Lagrangian mechanics? Isn't the classical mechanics of Newton just enough, where we define the forces and that's it? Well, you have to know that sometimes in a system can be very complex. Consider, for example, the pendulum. You see that the mass is attached to the thread. Now you have two forces, the force of the weight, so P equals m times g, but you also have the tension of the thread. How do you actually express this tension, Now we can do it by going in a polar system, expressing x and y in terms of r and theta, since r is a constant and theta is just the variable, so you have only one variable. Now, what if you had two pendulums, or other very complex systems? You see, the problem is when you have a force, you sometimes cannot define or determine what the actual force is. So the Newtonian mechanics actually had some limits with particular systems, and a new formalism was needed. This is why, after some times, another formalism appeared, which was the Lagrangian mechanics. Now in Lagrangian mechanics, we do not focus on forces, we focus on energy. And the Lagrangian mechanics in itself focuses on the principle of least action. So the principle of least action in a way states that if you have 2 points A and B, a particle, mass or anything, will move from point A to point B in a way that will minimize its action. This is in a way what nature always does. Consider, for example, a river. A river flows in a such way that the action or the energy it needs to produce is minimized, because everything is lazy around us. And this is the most efficient way to do things. But don't quote me on that, I actually very much preach hard work and discipline and grit. So never mind. Let's consider another example of an object falling. You see, the path is always the path that takes the least action. You'll tell me it's because of gravity. Yes, it is. Or a feather floating slowly and falling. You'll tell me, well, yes, because it's of air friction. I'll tell you again, yes, but it's also the least amount of action needed. The feather will not do high floating, it will not do a straight fall. It will do a combination of both that will actually minimize the action. Alright, we considered examples. We said what the Lagrangian mechanics is. Now, what does Lagrangian states in physics? Lagrangian is defined with L, so Lagrangian, is equal to T minus V, or T minus U, depending. T is representing, the kinetic energy, so the half m times the velocity squared, where the U or V stands for potential energy or utility energy, for some call it like that. Remember, L defines the action, an action that we seek to minimize. Now, why is it T minus U? An example just came to my mind. Suppose you're running on a treadmill, right? If you ever worked out. If you didn't, you should work out, whether you want it or not, but never mind. Let's say you run a treadmill. You will notice that if you run at 10 kilometers per hour, it will require a certain amount of energy. But if you run at double the speed, so at 20 kilometers per hour, you'll not just demand twice the energy, but far, far more for you who runs 20 kilometers an hour. And likely, you see that the speed is actually proportional squared to the energy, and the heavier you weigh, the more energy is required for you to run. Now, when it comes to the potential energy, the higher you are on the ground, for example, you are at 100 meters, 1 kilometers, or at the tip of the Mount Everest mountain, you will have a specific amount of potential energy, the potential energy you have. Now, when it comes to your Lagrangian, suppose you are running from point A to point B. Now, you see that you are running from point A to point B in a specific path, with a specific speed, and at a specific height. The motion in itself, whether you are on the ground level at 100 meter, at 1000 meter is the same. You go from point A to point B. So your Lagrangian in this case will be your kinetic energy minus your potential energy. So in this way we are focusing solely on the motion. Now remember, we actually want to minimize the action. The term minimize is often represented by a derivative equal to 0. This is actually the case also with the Lagrangian. There is an equation called the Euler-Lagrangian equation, which is this one. And it states that if the Lagrangian satisfies this equation, the action is minimized, and thus we fully describe the motion of our particle or system. Now we will not solve this type of equation analytically. It's 2023. It's numerical time. We will do a Python simulation, or rather Python implementation of the Lagrangian equation, and we will try to solve this equation for a very simple mass spring system, where we will define all the variables, kinetic energy, potential, and so on, and we will find the velocity and the position of a particle. Alright, so the Visual Studio Code interface is waiting right there, so I'll let it come and let's go. Alright, so here we are in our good old Visual Studio Code interface. In this specific problem of the mass spring system having a mass with a mass m and a spring with a constant k, we want to determine the position of the mass and the velocity of it at each time t. Now, we are going to import our libraries. We will be importing NumPy, SciPy, and SymPy. We don't usually work with SciPy and SymPy, but I find it very interesting to actually see what these libraries are capable of. We're going to use the ODE int to solve some equations later on, and the SymPy, since we are doing with symbolic mathematics. Alright, so here we imported the libraries. After importing the libraries, we are going to define the symbols and variables. You can do it very easily with the sympy.symbols. Then you insert the symbol t. You can do it also for m and k, specifying that they are positive constants. Okay. And then q. Now q is actually the position of the mass at each time. Right, so we defined with cm.symbols, q, and then we will specify the class as it being a function. So this means that q is in reality a function of t. If I go ahead and print q, and then run this block here, you see that it's q of t. If I, let's say, add another variable here, m, I rerun this, you'll see that it depends on t and m. Right, so let me remove this right here. Okay, we can also print k and m. You see that we successfully define our constants and variables. So these are constants, and this is our variable. Okay. Now, remember, first step was importing the libraries, second step was defining the symbols and variables, and then the third step will be to calculate our derivatives. To do so, it's very easy with SymPy. You do a sm.diff, you mention q, or with respect to t. If I go ahead and print dq dt, I run this code, you see that it successfully displays dq over dt, and same goes for the second derivative. This represents a velocity, so velocity, and this represents a acceleration. Alright, so let me rerun that. Okay. Then we define the kinetic and potential energy. Since we have a spring and a mass, well, the kinetic energy is, like always, 1.5 m times dqt squared. So 1.5 m times the velocity squared, like we did right here. And the potential energy is 1.5 times k times the position squared, which we also did right here. So let me do it here. We print out t. Here's our t, our kinetic energy, and here is our potential energy. Then we define the Lagrange with L is equal to t minus v. Again, if I want to print this, you'll see that here is our Lagrange. Okay, here we run that. We define our Lagrange. Now we will formulate the Lagrange equation, this one. So we will consider a non-damped system without any external forces. We formulate it with this equation right here. Now we first define this derivative right here. We differentiate L with respect to Q dot. This is what I did right here. So we differentiate L with respect to Q dot. I called it dl d dq. And then we just simply specify our equation. So L equation, so this one, is equal to simpi dot diff. So this one we just define across t. We differentiate this with respect to t minus sm dot diff L and Q minus this one. We then simplify our equation if there is need to, but I don't think in this case we need. It's a pretty basic equation to begin with. Right, let's see. Here is our equation. So this will be equal to 0. Alright. Okay. We run this. And then now here we're creating a functions for solving the Lagrange equation. Now let me go back here to the L equation. Now, you see that here we have this equation is equal to 0. Now, this equation is the same as this one, which is equal to 0. And we want to solve for this one, for the acceleration. Alright? We do it like so. Alright. Here we can see that we solve the L equation. So, this one, with respect to d dq, d dt, with respect to this quantity right here. If I go ahead and print Lagrange equation, let me actually print it down here. You see we have minus k over m times qt. Now again, see this equation. Now if we bring this quantity right here to the other side of the equation, we will have minus k times qt, and then we divide it by m, so we have minus k over m times qt is equal to the acceleration, this quantity right here, which is this one. And then we use a simpi.lambdfy. Now simpi.lambdfy in reality transform a symbolic equation into a function. Here, the resulting Lagrange Eq function is a function that takes the specified variables as input and computes the second derivative of the position with respect to time according to Lagrange's equation. So basically this is our acceleration in the form of a function that takes as input these parameters right here. So q, which is right here, the time here, and then the spring constant and the mass. Alright? And then here we solve our problem. So we initially define the initial conditions with the position and the velocity, the values of m and k, alright? Then you actually solve it with this function right here, ODE int, the one we imported right in the beginning, here from SciPy dot integrate import ODE int. This function takes as input another function, which is this one, and then the initial conditions, the time steps where we will do our simulation, which we define right here, with time points is equal to numpy dot linspace from 0 to 10 seconds, and some additional arguments right here, which are mval and kval. Now this function right here, system of ODEs, is actually a pretty handy way to solve ODEs in general in a numerical way. But before I can speak about this function, I want to introduce you to this principle right here. It's called numerical integration using the Euler method. Right, so you see how in numerical simulation we always use this expression right here to approximate a derivative. We say that this derivative right here is equal to yn plus 1 minus yn divided by dt. But we can express y of n plus 1 very easily. So here I have put some definitions. Now, in the case of our mass spring system, we want to convert this equation right here, this equation right here, we want to convert them into a system of ODEs. Okay? We can do this by saying that dq over dt is equal to the velocity, and then dv over dt, which is the same as the acceleration, is equal to minus k over m times q. So this is the same as this equation right here. Okay, so we have a system of two ODEs, very simple, where in one side we have the velocity dq over dt and the acceleration dv over dt, or the second derivative of dq over dt squared, and at the right side we have the velocity and the position q. So what we are going to do is compute the derivatives dq over dt, which we will be calling Vn, and dv over dt, which is the same as the acceleration, will be equal to minus k over m times qn. When we have this expression right here, we can plug it right here and right here. We multiply by our time interval dt, and then we add the previous value of q and v. Alright, so if we consider a basic example, suppose the initial state is y0, 1, 0. So here the first element represents the position, and the second element represents the velocity. And the time step of 0.1, and having k over m is equal to minus 4, so here it's actually k over m is equal to 4. Okay, so we have yn is equal to 1, 0, and then by using this system right here, this one, remember, yn is equal to 1, 0. So here this is equal to 0, and this is equal to minus 4 times 1. You see here, minus 4 times yn of 0, which is 1. Then we have dq and dt. We replace them here. We multiply them by dt, which is 0.1. And then we add the previous value of yn or y0, which is 1 and 0. We update the state and we redo the work over and over and over again. So this is basically what we are doing right here. We have here our y vector, which contains our position and our velocity. To compute the acceleration, we use the Lagrange equation function. So this one right here, let me go back. So let me actually hide this. And this one. We compute this one using k, m, and q that we have, using q, m, k, and t. Alright. So initially y will be equal to 1, 0. So this will be 1 and then 0. We replace these here, and then we return the velocity and the acceleration. So dq dt, and then ddq ddt. And we basically do this over and over and over again until we reach all the time points. So we extract then the solution in a type of a vector, where the first column will represent the positions and the second column will represent the velocities. And then we print very easily the results using a plt.plot, adding some legends and a grid. And we get this plot right here. Alright, so let me actually show here the image at the same time. Alright, so you see here, at t equals 0, the position is at 1, for example, so right here. And then we leave it. The initial velocity is 0. And then it oscillates back and forth between a and minus a. Or in this case, between 1 and minus 1. And so does the velocity. It is maximum when the mass is at the coordinate x equals 0. And it is equal to 0 when it reaches the minus a or the a values. Or in this case, 1 and minus 1. So you can see here, at 1 it is 0, at minus 1 it is 0 again, and so on and so forth. Alright, so this is what I wanted to show you with this code right here. Hope you liked it. Hope everything was clear. And yeah, thank you. Hey, thank you for watching this video till this point. Hope you liked it. I very much enjoy making these types of video, though a like or a subscribe will help me and motivate me tremendously. Feel free to check my other videos, I got some Python tutorials, but also some educational math. And I hope to see you on the next video, and peace!